So good morning, welcome back. And yesterday we talked about the first difficult part of this course is shear. Okay? Yes, the shear. The shear, firstly, you will see a bearing force, because when you have a shear loading, you must have a opposite force. So you must be stop something. The material must stop the force. So when you have the stopping the force, you can call it bearing force. And then if the bearing force divide the area that the force acting on it, it becomes bearing stress. Okay? And the important feature is that the loading must be perpendicular to the area. Okay? So for example, if you have the Y shape here, and then you notice that the Y shape material apply half P on the bolt, and then the bolt will stop it, right? So the half P and half P acting on the white area. So half P divided by area will be the bearing stress at this position. Okay? Again, for the region 3, the bearing stress at region 3 is half P divided by this white area. Okay? And for the other part of the gray material, right? The gray material acting P on this area, on this region 2. So P divided by the area AB here, and you will see this is P divided by AB2. Okay, so you can notice that this bolt has two regions. At this case, two regions with the bearing stress, and the middle has almost double bearing stress. All right, so this is bearing stress. And then you notice that if you have a force with the opposite side, which means that this intersection must has the force, shear force. Okay, try to kind of cut the bolt, right? So this force will give the area which parallel to the area, parallel to the load, is the dividing area. Okay, so as you can see, if you want to see the force at this section, you can cut it. Okay, you can cut it, and after you cut it, you can do the what does that mean? Force balance. So if you have P and you cut out of the gray part, you can see half P and half P. So to make this Y-shaped blue material stay at the same place, right? So you can see that this red region area has the shear force half P divided by this area become the average shear stress. Okay? So that's the shear and bearing stress definition. And then we talk about direct shear and indirect shear. All right? And then you can see that the previous case are double shear, and the easier case is single shear. And you can notice that actually the concept is all the same. Okay? If you want to see the force, you just cut it and then separate it, and then you do the work balance, and you can have the force on the area, and then you divide the area, you will get the shear stress. And also indirect shear. Indirect shear just let you know that if you twist a bar or make a distort a bar, you also give the indirect shear to make the element, the material element on that device. Previously it is square. After you do the loading, it become a shape like this, 平行四边形. Okay, so yeah, and also very important concept that even if you only apply normal force, you're still generating shear for the material at certain angle. Okay, in the 90-degree angle, XY axis angle, no, there's no shear. But if you see another angle, the material still suffering the shear. Okay, so we will talk about this in more detail later. Okay, and then we talk about the shear element, shear stress on an element. Shear will always come in pairs. Okay, because we want to make this element stay there and not rotating. Okay, so if you see one of this or you see one of this, you can always find the other three. Okay, and we also talk about sign convention of the element. If the element, if the shear stress acting on a positive area, and its shear stress is along positive direction, also plus times plus become plus. Okay, so you will have the positive sign convention. And how we get how we identify a surface is positive or negative. You can imagine that you enlarge this cube. Okay, enlarge this cube, and the surface will push to which direction. Identify its positive or negative. For example, this one, if you increase the volume, it will move to the positive x, which means that surface is x, positive x surface. Okay, and then Hooke's law in shear also similar to the normal Hooke's law. And then we talk about this example, and then we talk about how we determine the bearing stress at the pin. Okay, due to the strut. Okay, and let's continue. All right, so the strut shear.
画面好像没有调整到镜上。
谢谢。我刚不是 share 了吗？我刚明明就 share 了，对不对？真的是很奇怪呢。好，谢谢佑轩。这样看得到我们的画面了吗？
这样有了。
好，谢谢。那我们再来试试看。我刚明明就按 share 了，这样可以了吗？
有。
谢谢。还好，刚刚都是在前情提要，非常感谢你。All right, so let's continue. Okay, so now previously we talked about strut going to hit you right in this view, and the pin stop it. So the pin will stop the strut. So using two area, these two red area. So you can see either so you can see this area suffering half P. Okay, because this place only has half P this place half P, this place half P, right? So half P divided by the area, and you notice that the forces go out of the screen. So this area is perpendicular to the force, so it's bearing stress, right? So you got 125 megapascal. And then you notice that the pin is going to hit you, right? Because pin stop the stroke, but the force doesn't still there. It's still there, right? So the pin is going toward you, but gusset help you to stop it, right? So gusset also has the bearing stress. So gusset half P divided by Tg times dP, and you got 100 MPa. Okay, now, so which thing stop the gusset? Which thing? So you can notice that the P here is 40 degree. So when the G gusset stop the P, there will be two component of the stress, component of the force. The first one is downward, right? Downward. The other is horizontal. Okay? So, and you notice that the theta is 40 degree. So we all know that. Wait a minute. We all know that the horizontal force is P cosine 40 degree, right? And the vertical one is P sine 40 degree. So do we need to consider the P sine 40 degree? Actually, no, because we have a Earth on the ground, right? So P sine 40 degree. The base will help you to stand that. Okay, so to bury it. Okay, bury it. So what force will causing the shear P cosine 40? P cosine 40 degree, because you can notice that when you push the P sine 40 degree is stopped by the ground, but it still have the horizontal to make it move forward, okay? To make this thing move forward. So what kind of stuff will stop the device going forward? For anchor bolt, right? So you can see sigma B between the anchor bolt and the base. Okay, so you can see that this is a base. This is a base. Okay, this one. This is a base, and 4 anchor bolt holes on it, and you can notice that the bolt will stop the horizontal component. Okay, so you can see this force are going to push forward. Okay, so this push forward P cosine 40 degree will stop by what? By this 4 blue rectangle. Okay, so the fourth problem, sorry, I tried to make it systematic, so I talk about bearing stress altogether. All right, so this is 4. Anchor bolt will stop the horizontal force. All right, so sigma B P cosine 40 degree. And 40 degree, P times P, divided for 4, right? Because you got 4 anchor bolts. And the area for each anchor bolt, the bearing area is TB times D bolt. What does that mean? You see here, D bolt is the bolt width, right? And the thickness of the base is TB here. So this blue rectangle is TB times D bolt. All right. So now let's continue. 5, 4, 0, 0, 0. Cosine 40 degree. Divide by 4. Okay, 0.008, 0.012 equal to 107.7 megapascal. All right, so now everything is stopped, everything safe, right? The force all stopped by the ground. Okay, so you can see how the force transfer from the top and then to the pin, to the gusset, to the anchor bolt, and also straight to the ground. All right. Now this is the what to say, bearing stress. So now let's talk about shear stress. When we talk about the shear, you must have the bearing stress. Bearing stress has the opposite direction, right? Opposite direction. So you can notice that the in area between that is 我关个门好了，我好像发现别人觉得我太大声，那我也小声一点好了。好，这样应该可以，反正大家应该也听得到。Right. So, second one is are using green. Okay, green. The second one is tau mix. Tau mix in pin. So you notice that there must be something going on in this stopping things. So you must see there's some pin has the shear. Okay, so let's take a look. All right, so you can notice that these blue going to you, but the gusset stop it, right? Pin stop it. So okay, you can see that there must be a interface that has the shear force. So you can see that it must have some shear acting on the interface. Okay? And then I'm going to determine this tau mix pin. And I will explain to you why it's called tau mix. Why not just tau? I will explain to you later. But now we are going to just trust me. Okay, this is tau mix, and I will prove it to you later. So I believe you know what is the force is. P divided by 2, right? But now you are going to divide the area that parallel to it. So this is pi d square pin. Whoa. Pin. And divide by 4. All right. Okay, and it is 54002 divided by pi 0.0182 divided by 4. It is 106.1 megapascal. Okay, that's it. So you can see that the pin is shearing, under the shearing, right? Next, I'm going to show you why this is tau max. Why not just tau average? Because when we talk about, I talk about that the material may has different stress state at different position, different point. So this is mixed. The other place may not have the stress or may not have such high stress. All right. So I will give you a comprehensive example in the next page. Okay. Let's go. When we see the material or the system through this direction, okay, and you will see this figure, right? And then the force is like this, right? So you will see, if you see from the top, okay, this is the top view, okay, top view, and then this is S, strut, right? And this is gusset, right? And this is pin. I believe you know that, right? Then you can notice that the force, two blue wall will have half P, right? So you have half P evenly, half P evenly distributed on this surface. Okay? And then you will notice that wait a minute. Anyway, you will notice that this actually has the resultant force P divided by 2. P divided by 2. Okay, so this distribution load has the resultant force half P. Okay, and then you must know that this force must has similar situation in the G here. Okay? And of course, this also half P with the resultant force. Okay? And it will help you stop there. And of course, this is T, this is T, and this is TG, and this is TG, and this is D pin. Okay? I guess I believe you understand what I'm drawing, because all these we have learned that in the bearing stress part. Okay? So let's talk about the shear stress on this pin. Okay? The reason why we plot this force diagram is because we are going to see the stress distribution or stress condition at this pin. Okay? So now, if we are going to a assume that this P is connected, right? But we are going to see the shear stress. So the shear stress. Before shear stress, we need to know the shear force at certain plane. So, which plane? The green part, right? The green part. Actually, these two is symmetry. Okay? So green part here is what we determined in the previous page. But actually, we have certain other parts like this, right? This, right? So, because we want to see the pin, shear stress in the pin, so we just cut the important surface. You can cut here, cut here, cut here, cut here, cut here. It's okay, but you can do it by yourself in your house. Okay, back home, we just took two important surface. Okay, to examine the force, shear force and shear stress at the interface. So I cut here and here. Okay, well, you cut here and here are all the same because there's symmetry, right? So I cut here and here. So I want to see the green stress, shear stress at the green plane and light green plane. Okay? So let's examine that. Previously, we know that this one is, if we cut it, you notice that half P is going up. So you need to have a half P going down, right? And it also tells us this green area has opposite but the same value, half P. So that's how we get half P green shear stress in the previous page, right? That's exactly the same. You know that. So we say this is one of the shear stress at this pin. But let's take a look. The light green. After we cut it, okay, you see half P, hey, they are the same. So actually they cancel each other. So actually no any shear force at this position. If you cut here, you will have the same situation here, here, here. They all has the same situation. So this position has zero stress, shear stress, zero shear stress. Okay? Maybe you will think, however, maybe you will have the moment. Well, this is later, okay? We are not considering moment. Moment won't causing shear at this plane, at pin, okay? So you can see that, okay, indeed, in between this region, pin has shear stress equal to 0. But here, they have maximum shear stress, okay? Along this region. You can go back home and cut here, and here, and here. You will get exactly the same result like I did. OK， 好，这边中文讲一下有点复杂哈。我们刚刚说 pin 为什么是 tau max 呢？为什么会有 max？ 难道有其他的比较小的吗？对的。好，那我们来仔细的看一下。所以这就是我画这张图的原因。然后呢，我们来看一下，就是我们要切 pin， 切开 pin， 我们才可以知道 pin 里面的力量，好，剪力。那我们就开始剪。那剪第一个是深绿色，还有浅绿色。那这边切这边跟切这边其实是切左边跟切这边其实是一样的事情，因为它是对称的嘛，哈。所以我切这边跟切这边，然后切这边，好，切深绿跟浅绿的部分。那深绿的部分切下来以后，我们刚刚就可以看到用右边来做力平衡，我们就会发现。哦，这边是P，那这边一定要有P啊，哈，所以说对面的P也会就是互相抵消掉嘛，因为它最后要接在一起，这两个面最后要接在一起，好， 所以说这边往下的话，对面就一定往上，然后一样大小，所以2/P会 P 作用在这个深绿的截面上。那这也就是为什么我刚刚说2/P 作用在这个深色截面上，它是最大的。那我们来看有没有其他比它小的？有，我们看这边绿色的、浅绿色的，我们浅绿色来看一下，这个浅绿色要用多少的力才会让这个东西不要跑来跑去啊？不用啊，因为它2/P往下，2/P往上，它本来就已经平衡啦，所以这边不会有剪力。但是同学可能会说，这边它会转，对，所以其实这边其实会有更复杂的弯矩，但是不用担心这个弯矩，它不会造成这个 pin 的剪切应力，所以那是以后的事情，我们之后再考虑，好吧？那但是现在我们看这个剪力的话，我们可以发现，v 等于0啊，那所以其实这边的涛就不用任何的力在这个截面上，我们就可以维持这个东西的平衡了。OK， 所以说这边是没有剪力的，没有剪力的话，当然就是 shear stress 等于0，好，那就是比较可能是 minima 吧，shear stress minima。好，那如果这样的话，我希望大家可以听得懂这边在讲什么，有点复杂哈。Anyway, next one is the fifth one. Fifth one is well, 黄色。So this is fifth. So it is a little bit light color. Fifth. The fifth is tau in anchor bolt. Because you have the bearing stress here, you must have the force. Try to cut it. P cosine 40 degree. Cut it. And try to cut it. And we are going to use this 4 yellow circle area, because this area is parallel to the force. Okay? So tau bolt equal to P cosine 40 degree divided by 4. And pi D2 bolt divided by 4. And equal to 54000 cosine 40 degree divided by 4. And pi 0.0122 divided by 4, which is 91.4 M/Pa. Okay, that's it. So each bolt suffered 91.4 megapascal shear stress. Okay? So the stress is going to shear it. And then we can notice that if the bolt material itself cannot stand for 91.4 megapascal, it will shear break. Okay, so we need to select. So this is how we select the material. So when we know that, we know how heavy, how the load it is, and then we can using this to calculate the shear stress or any other normal stress. So you can know that what kind of material we choose. Okay? So this is a little bit difficult, I know. But all you need to do is you need to have right concept, right knowledge, correct knowledge about how you draw the force and how to balance it and choose correct area. Okay, choose correct area. Remember, bearing stress area is perpendicular to the force. Remember, shear stress area is parallel to the force. That's it. Easy, actually. Okay, the next few examples are very simple. Let's go. Okay? This is a little bit easy. Okay, there's a punch. Punch. We're going to punch the hole. Okay, there's a hole on it, and we are going to determine tau average in the plate and sigma c in the punch. Okay, easy. Okay, tau average in the plate and sigma c in the punch. And C means compression, right? Because you are going to compress it, okay? And the first one, tau average. The two examples are easy, okay, compared to the first one, okay? P divided by the area. So what is the area of the shear stress for this plate? Here, right? You see, you can see there must be, you see, this area is where the force acting on and also parallel to the force, 平行, right? So this is pi dt, okay? 0.008 pi times 0.02, 1218.8 pi. Okay, easy. And how about the punch, compression on punch, sigma c, right, minus P divided by A because it is compression, right, equal to minus 11000 pi 0.02 square equal to minus 350 m pi. Okay, so that's relatively easy, right? Now, I'm going to say something about this, the minus side here, okay? Normally, yeah, I should write down this, okay? How about this? If do you see the difference? I will say these two things are equilibrium, okay, the same. Because you see, sigma c means compression. So we must know that 350 megapascal is compression. But if you just say sigma, which means that you don't define the direction of the sigma, so you should put minus. So both of them are okay, because as you know that sigma positive is tensile, negative is compression. So if you define the direction, the value should be okay. Okay? You don't need to say the minus sign here. So either these two are okay. Right? Okay. Next one is even easier. Next example are even more easier. But just going to tell you one simple concept that may be useful for later. You know, we cannot put a lot of difficult problems to scare you. So the previous one is quite difficult, but this one is simple, and next one will be even simpler. All right, next one. So there's a stuff like this, and then you have a plate on top, and they are going to ask about the shear stress, average shear stress of this material. Okay, and you see that this material suffering a shear force on the top, V. Okay, V. And they just ask us average shear stress. Wow, very easy. Don't worry about it. 1 tau average equal to V divided by area. Area is AB. That's it, simply as that. Okay, the important part is the second one. Second one is horizontal displacement D. So if you have a side view, you will notice that it will go to the right, right? And then you've noticed I want to ask the D. What is D? Okay, D equal to H, the height, right? Times tangent gamma. Okay? I believe you know that, right? Tangent gamma. How can we get this? We have a triangle here, right? So tangent gamma to get the D times H. Now this is a little bit. Now I'm going to talk about the reason why I choose this very simple example, because tangent theta will approximately equal to theta, and sine theta will approximately equal to theta if theta is small. Okay, that's the important concept I would like you to introduce that, because sometimes we use tangent sine, and usually we are talking about very small strain, less than 1%. Okay, so typically we can use this, and also important that the theta is radian. Okay, radian. So it will be shear strain. Okay, so now let's continue solving this problem. Assume shear modulus is G. You see, we cannot get the answer without assuming that average divided by G. So it will be V ABG. So D equal to H times tangent V ABG. So it will be approximately H times V ABG. Okay? 然后 and when gamma is small, which is typically the case. Okay? Typically the case. Right, that's it. And next week I'm going to introduce the final few pages. Well, not final few pages. Next week I'm going to introduce how we design a material. Okay, either choosing different material, either choosing the diameter of the device or size of the device to prevent it from break or fracture. Okay. Okay. So thanks for coming, and I will see you next week. Thank you. If you have any questions, just come here. Thank you.